Hello and welcome to the presentation of the paper towards line-restricted dispatchable feeder using probabilistic forecasts for PV-dominated low-voltage distribution grids. I am Dorina Werling from the Karlsruhe Institute of Technology, and my co-authors and I are happy to introduce our current research on the line-restricted dispatchable feeder. The motivation of the considered scenario is that the energy transition not only leads to a rising electrical energy demand, but also requires the development of a fully renewables-based energy system. To supply this rising demand, we need, among others, a massive integration of rooftop PV installations. For example, the German government plans to use each suitable rooftop for PV power generation. Such a PV-dominated scenario introduces new challenges in the low-voltage distribution grid. One of these challenges are line overloadings, especially at noon when the PV power generation is at its peaks. To mitigate such line overloadings without curtailing the PV power generation or doubling the street line capacities, batteries and appropriate battery management strategies are necessary. Therefore, we propose to model each house as line-restricted dispatchable feeder, which we will refer to as LRDF in the following. The novelty of the LRDF is the consideration of the line restriction, while also considering the uncertainty inherent in the presumption via probabilistic forecasts. So the rest of the talk is structured as follows. First, we introduce the LRDF. And afterwards, we will describe the simulation setup for evaluating the LRDF and present its results. And finally, we will summarize the findings and give an outlook on further research questions. So what is the LRDF? From the system side, the LRDF consists of two components, an inflexible and volatile, and a flexible but energy-constrained component. We consider a domestic house with the fully with PV panels covered rooftop as inflexible component and a domestic battery as flexible component. Both components are connected via one bus to the grid, and this architecture is the dispatchable feeder. The novelty of our approach is that we consider the line restriction between the dispatchable feeder and the grid, and together we have what we call the line restricted dispatchable feeder. As you can see in this picture, we simplify the scenario of a whole street to a one-house scenario. We do the simplification to evaluate the effect of a single LRDF without the interplay of multiple LRDFs. That also means that the line restriction corresponds to a single house share on the street line capacity. As the name implies, the aim of the line-restricted dispatchable feeder is to reach dispatchability of the considered system while respecting the line restriction. Thereby, the term dispatchability refers to the capability to strictly follow a day-ahead dispatch schedule for the next day. To reach this dispatchability, the battery management of the LRDF can be described by a hierarchical optimization problem with three stages. The first stage calculates at noon an offline dispatch schedule for the next day. As input, it gets probabilistic forecasts of the presumption in terms of quantiles and cumulative distribution functions. The second stage then adjusts this dispatch schedule by considering updated forecasts and the actual state of energy of the battery. It is an hourly rescheduling, and it describes a typical model predictive control problem. The third stage calculates the actual dispatch in real time based on the results of the second stage and the actual presumption values. Thereby, all of the stages consider the line restriction, which is an inequality constraint on the power output of the LRDF. The optimization problems are NLPs. For example, here you can see the mathematical description of the first state optimization problem. And as you can see, there are a lot of variables and expressions, and that is why we don't go further into the detail of the mathematical description of the optimization problems. But if you're interested in it, you can check out our paper. We will continue with looking further into the simulation setup for evaluating the LRDF. And for evaluating, we use the real-world data set provided by Ausgrid and focus on 3 weeks. Ausgrid is an Australian electricity distributor, and the dataset consists of domestic load data as well as PV power generation data. Since the dataset is from 2013, we scale the PV power generation data with 3 to account for the efficiency increase of PV panels and a fully with PV covered rooftop. The probabilistic forecasts are generated by applying the nearest neighbor quantile regression filter. And for evaluation, we focus on the 2 main characteristics of the LRTF. So the first one is the inclusion of the line restriction. And for evaluating the impact of the line restriction, we compare the results of the LRTF with the results of a dispatchable feeder without line restriction. The second characteristic is the consideration of the uncertainty via probabilistic forecasts. And for evaluating the impact, we compare the results of the LRDF with the results of a line-restricted dispatchable feeder using a perfect and a deterministic approach. So the perfect approach uses the actual presumption values in the first stage optimization problem and thus refers to the best possible solution, while the deterministic approach uses median forecast of the presumption in the first stage optimization problem and thus does not consider any uncertainty. As evaluation metric, we consider the minimum possible line restriction because the smaller the line restriction can be set, the more houses can be served via the street line and the less line overloadings occur. It corresponds to the maximum absolute peak of the actual dispatch. So first, we want to look further into the results for evaluating the impact of the line restriction. And here you can see the dispatch schedule of the LRDF and the dispatchable feeder without line restriction for an exemplary week. As line restriction for the LRDF, we choose the minimum possible line restriction, which is in this week plus minus 2.7 kilowatts, what you can see here in this orange dotted line. The maximum absolute peak of the dispatchable feeder without line restriction is plus minus 4.9 kilowatts, what you can see here in this green dotted line. So what we see is that the LRDF respects and adapts to the line restriction by cutting the PV power feed-in during the day. In correspondence, the battery of the LRDF charges to a higher state of energy during that period compared to the dispatchable feeder without line restriction. So the next result we want to look further into is the evaluation of the impact of the probabilistic forecasts. In this table, you can see the minimum possible line restriction with respect to the best possible solution, which is the perfect approach. And when we compare the LRDF and the deterministic approach, we see that the LRDF is at least as good as the deterministic approach, and thus probabilistic forecasts can improve the line usage compared to the deterministic approach. And the second result we see is that the performance of the LRDF depends on the considered week. So in week 3 and 1, we see that the LRDF reaches over 80% of the best possible solution. And in week 2, it only reaches 64%. In this week, we see that the actual presumption values do not lie within the ranges of the probabilistic forecast. That means that the quality of the forecasts play a role, which is not a surprising result. Concluding the findings, we see the results show that the LRDF can improve the line usage compared to a dispatchable feeder without line restriction, and that the LRDF can enable smaller line restriction than a dispatchable feeder with deterministic forecasts. As said before, we simplified the scenario to a single house scenario, and this equals a scenario with multiple houses with a fixed share on the street lines capacity. As these results are really promising, we would like to extend it to a multiple house scenario with a flexible share of the street lines capacity. And this can be achieved by the joint optimization of the multiple houses coupled via the line restriction. So with that, I would like to say thank you for your attention, and if you have any further questions, we are happy to answer them.